Hey everyone, welcome back, and today let's solve Leetcode problem 2684 titled Maximum Number of Moves in a Grid, the daily challenge problem on Leetcode. So we're given a zero-indexed m by n matrix grid consisting of only positive integers. We can start at any cell in the first column of the matrix and traverse the grid in the following way. From a cell row column, we can move to any of the cells row minus 1 column plus 1, row column plus 1, and row plus 1 column plus 1, such that the value of the cell that we move to is strictly bigger than the value of the current cell. We need to return the maximum number of moves that we can perform fitting these constraints in our input grid. So in example 1, they actually give us a nice image to better visualize how this would really look like, and they say that we can output 3. Why is that? Because we can start at the left top cell, 0, 0, and we can make the following moves. We can go from 0, 0 to 0, 1, which is row and column plus 1. Then we can go from 0, 1 to 1, 2, which is row plus 1, column plus 1. And from 1, 2, we can go to 2, 3, which is row plus 1, column plus 1 again. And we cannot go further from there because anything else neighboring would have a value that's less than this, okay? And they also explain how it can be shown that 3 is the maximum number of moves that can be made regardless of which cell you choose to fit the constraints, and so we'd output 3. In example 2, we have the following grid. It's a 3 by 3 grid, and we'd output 0 because starting from any cell in the first column, we can't actually perform any moves, right? If we started from 3, we wouldn't be able to go anywhere. 2, 1, and 2 are all smaller than 3. If we started from 2, we wouldn't be able to go anywhere. 1, 3, 4, they're all 1, and 2 are both smaller than 2. And if we started from 4, we wouldn't be able to go anywhere because 2 and 1 are also smaller than 4. Right? So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to solve this problem efficiently, we're going to first use a 2D list to actually store the maximum moves possible to reach each cell. And like we do for most BFS traversal algorithms, we're going to use a queue or a double-ended DQ in Python for the actual BFS traversal to explore the grid level by level. And we'll also define a list of directions to easily move diagonally upright, simply right, and down right. And we'll first start from all these cells in the first column, and we'll try to move towards the right. Right, and we'll use BFS to explore these cells and actually update the maximum distance or moves as we actually traverse the grid. And we'll keep a running count of the maximum moves found across all the different cells as we traverse through the input grid. Okay, so with that out of the way, let's just go ahead and dive straight into the code here. I'm going to have kind of an extra line of code just for best practice. I'm going to say from collections import the DQ data structure. It's pretty self-explanatory. I think that's how you spell DQ. We're simply getting the DQ data structure from collections, and already, although this module or package is already installed on Leetcode, just for best practice, I like to do this a lot of the times for problems where I need this data structure, right? And again, why do we need a DQ? Because it's efficient to actually perform BFS, because it allows us to effectively append and pop from both ends in a constant time, which is awesome for queue operations and BFS traversals. Right, so once we get that out of the way, let's just go ahead and dive our m and n, or sorry, define, not dive, to be equal to the length of the grid and the length of the grid at index 0 respectively. We do this for like almost every single matrix problem. M is going to be assigning the number of rows, and n is going to be instantiated with the number of columns. Okay, and this is just for easy access to actually keep track of the grid's dimensions throughout our solution as we traverse through the input. Okay, once we do that, now let's actually initialize our directions. Okay, this is going to be an array. I'm just going to call it dir, and it's going to be an array of tuples of length 2 containing all the different directions we can go from the current cell as we traverse through the input. So first we're going to have -1, 1. The second tuple of directions we can go is going to be 0, 1. And finally, we'll have 1, 1. Again, what does this mean if you're new to matrix problems? -1, 1 simply says that we're going to go diagonally upright. 0, comma 1 is going to say that we go straight right, or just right in general, and 1, 1 is going to tell us that we go diagonally down right. These are the potential different directions we can go from each cell in our queue, like they talk about in the problem. We can go row minus 1, column plus 1, row column plus 1, and row plus 1, column plus 1. Okay, so once we do that, now let's actually initialize our distance to the array. This is going to be 0, and this is some Pythonic stuff here, times n for, I'll just use a iterator, or sorry, a underscore as my placeholder for my iterator, because we don't actually need to use this anywhere else for this for loop. So in the range of n, of m, where again, n is the number of columns and m is the number of rows. Okay, so this is again going to be a 2D list, and it's going to have the same dimensions of the grid, right? It's going to be n by m, and each element in that disk is going to be initialized to 0. Why is it initialized to 0? Because that represents the maximum moves we can make to actually reach that cell. It's going to be instantiated or initialized to 0 because we haven't done anything just yet. We haven't actually updated it because we haven't traversed through the input just yet. And now for our main data structure for the BFS traversals, I'm going to define or declare my double-ended queue data structure, and I'm actually going to initialize that in the variable called q. You can call it whatever you like. I'm just going to say q for easy access, and it's going to have a tuple, and it's going to have one kind of base case or root, right? What is that root, you say? Sorry, I think I formatted this a little bit weirdly. Let me kind of refactor that. It's going to have a, okay, that is a little bit better. It's going to have I, comma 0, and we're going to use some list comprehension here. Again, pretty Pythonic, but it's pretty straightforward. It's going to be I, comma 0 for I in the range of m, where again, keep in mind, m is the number of rows that we actually have. But why do we need this? Why do we need this? What does this actually do? This queue is going to basically first be instantiated or initially populated with all the cells in the first column of the grid. And we have to do this because, again, we need to start our BFS traversal from that leftmost column. And so it's going to be initialized with all of the cells in that initial or first column of our input grid. Okay, so once we do that, now we're going to initialize our max moves. And pretty self-explanatory, it's going to be initialized to 0. What is this max moves going to keep track of? It's going to store the maximum moves, again, that we find during this traversal. Pretty straightforward, all right? So now we can have our main BFS traversal. So while a queue is still non-null, essentially that's saying while we still have reachable cells in this BFS traversal, so until it's actually non-empty, or empty rather, we'll have variables I and j to be equal to the pop left of the queue. Okay, and again, pop left is simply popping from the left side of the double-ended queue in constant time. That's why DQs are so helpful in BFS and DFS traversals. But and I and J are basically going to represent the current cell that we're actually popping off of and exploring the current cell's row and column, their cell value, if you will. Okay, so now we'll actually loop through our directions array. So we'll say for dx and dy, dx and dy in the directions array, right? Again, we want to basically iterate over the 3 possible directions using that for loop of the directions array. We have to set x and y to be equal to dx plus I, or sorry, yeah, actually that works, and dy, plus j. Why is it that? Because we need to calculate the next cell's coordinates, or the new coordinates, using those dx and dy iterators, because that's what we're using to iterate over the new directions that we can possibly go to from the current cell I and j. Right? We have to add the current potential changes in directions, dx and dy, to our current cell value, or coordinates I and j, which is the current cell's coordinates as we pop left from the queue in this iteration. Okay, so once we do that, now we actually have to have our main boundary check. So this is going to be pretty lengthy. It's going to be pretty weird, but we always have a standard boundary check for all matrix problems. Feel free to just kind of fast forward as I type this out pretty slowly here so I don't make any syntax errors here. I'm going to explain it once I'm done actually typing the entire line. Okay, so if 0 is less than or equal to x, which is within m, and 0, again, similar logic, is in less than or equal to y, which is less than n. And this is where we kind of get something more local to the problem itself. And grid at x at y, right, our new cell's coordinates, if that's actually strictly greater than grid at I and j, our current cell's coordinates, not our new ones, right, as we pop left on line 11, and distance, at xy, get our new cell's coordinates, if that's less than distance at ij plus 1, okay, then this is kind of, again, our boundary check. What does this do? Why is this so lengthy? What are all of these guys kind of saying here? What's the importance of them? Okay, what do we do here? We have to check if the next cell, xy, is actually within the grid boundaries. If it's and, we also have to check if the cell's value is strictly greater than the current cell's value, because that's how kind of moving around is defined to be in this problem. It says that our next cell should be strictly bigger than the value of the current cell. And we also have to make sure that the distance to the next cell is greater than the current distance. That's what this guy is saying right here, and we're adding 1 to kind of add on to that value, right? And if that's the case, we can set distance at xy to be equal to distance at ij, plus 1. Right? What do we do here? If all of these conditions are met, we can update these distance of the next cell. We can add 1 to that, basically extending this path. We're basically adding 1 from the distance at ij to the new cell using that directions iterator's distance at xy, because we're extending the path by 1, or we're increasing its length by 1 as 1 more move. And once we do that, now we can update our max moves. So max moves is going to be equal, because we're trying to maximize it to so the maximum of course, itself, because we don't want to make it smaller. We want to keep it as optimized and large as possible, and distance at x at y. Okay, so we have to basically use the maximum of these two values, either the now next new or current cell distance at xy and the original max views value before actually updating it. And now, after we do that, then we can append to our queue the new coordinates xy, and I'll actually put that in a separate tuple so it actually has a sustainable operand type. So we have to actually add the next cell to that queue to continue on to the next iteration of the BFS traversal. And ultimately, outside of this while loop here, once queue does not have any more nodes to actually process, we can simply return the max moves that we actually updated and calculated in these BFS traversals or iterations level by level. So unless I made any syntax errors here, this should be accepted. And as you can see, this is just about as efficient as you can get. So overall, what does this code actually do? What is the importance of every single line of code here? Okay, so we're going to use BFS, or breadth first search. And how do we do this? We simply traverse the grid from the first column to the last column, and we have to explore all the different paths, and we kind of manually update the maximum number of moves we can make at every single level or iteration, at every level of all the different paths in the input grid. And the distance array also makes sure that we don't revisit cells unnecessarily, and that all the new cells have cell values or coordinates that are within the bounds and have strictly greater values of the input grid. Okay, so for the time complexity of this program, this is going to be a big O of m times n solution, where again, m is the number of rows and n is the number of columns. And why is that? Because we visit each cell at most once during our BFS traversal. And the space complexity is also going to be big O of m times n, or mn, due to that distance array and also our queue needed for all the different nodes in the BFS traversal. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.